Hi all. This is our third and last part of video lecture about X-ray image classification using CNN to classify the chest X-ray image as normal image or images having pneumonia. So let us continue with our lecture. In previous two parts, we talk about the CNN and our data set that we are using for the purpose of training the model and testing the model. We just summarize it quickly. We are using training data set that contain in total 5,216 images, out of which 1,341 normal images and 3,875 images are of pneumonia. Using this data set, we will train our model. Our testing data set contains 624 images, out of which 234 images are normal X-ray images and 390 are X-ray images identified as pneumonia. The convolution layer contain two convolution layers. Each of them are having convolutional subsamples followed by pooling layers. Finally, we have flattening layer followed by the fully connected layer. It is important to note that we are using two hidden layers here. The first hidden layer contains 128 neurons and second hidden layer contains 64 nodes. We use ReLU activation function for our hidden layers, and the output layer is having single node as our output is of binary type. At output layer, we are using sigmoid function. So let us continue ahead and see how our model actually works. All right. So let us create the model. Here we created the model, even we saw it in last lecture, where we specify input, which is input layer, and output is our output layer that we have defined earlier. And you can observe here, image dimensions are also defined. They are 150 by 150 pixels. This model is compiled, and when we compile, we pass optimizer, loss, and matrix as our parameters. We need to understand about these three parameters. Let us talk about optimizer first. First is the optimizer. We are using Adam as our optimizer. Here the question is, what is optimizer, why we use it, and why we choose Adam as our optimizer. Okay, so let us understand that. I will explain this in brief. Actually, how we should change your weights or learning rates of our neural network to reduce the losses is defined by the optimizer we use. Optimizers are algorithms or methods used to change the attributes of our neural network, such as weights and learning rate, in order to reduce the losses. Optimizers help to get result faster. Optimization algorithms or strategies are responsible for reducing the losses and that provide the most accurate results possible. Full form of ADAM is adaptive moment estimation. It works with momentumous, momentumous of first and second order. So it is first or second order momentums, and ADAM is a replacement or optimization algorithm for stochastic gradient descent for training deep learning models. Adam combines the best properties of the ADA-grade and RMS prompt algorithm. These are two important algorithms that are normally used as optimizer, and that provide an optimization algorithm that can handle sparse gradients on noisy problems. There are different optimizers for different kind of problems. Some of these optimizers, apart from Adam, are SGD, that is stochastic gradient descent, which is short form of stochastic gradient descent. Then we have RMS prop, then ADA delta, ADA grade, ADA max, etc. These are various optimizers available. Second argument in compile function is loss. The purpose of loss function is compute the quality that compute the quantity that a model should seek to minimize during training. There are three categories of losses. First is probabilistic losses, second category is regression losses, and third category is hinge losses. That is for classification purpose. Here we are using binary cross entropy loss, which is of the category probabilistic loss. Third argument is compile function, and that is matrix. A matrix is a function that is used to judge the performance of a model. Matrix functions are similar to loss functions, except that the results from evaluating matrix are not used when training the model. It is important to note that we may use any loss function as a matrix. Matrix are categorized as accuracy matrix, probabilistic matrix, regression matrix, classification matrix, image segmentation matrix, and hinge matrix. We are using accuracy matrix in our case in this particular example. Here we are using three triggers while we train the model. These three triggers we will understand one by one. As you can see here, the first trigger we are using is module checkpoint. The second is the reduce LR on plateau. LR stands for linear regression, and third one is the early stopping. First we will understand reduce LR on plateau. Models often benefit from reducing the learning rate by factor of 2 to 10 once learning stagnant. So for this purpose, reduce LR on plateau function is used. This callback monitors a quantity, and if no improvement is seen for the patient number of epochs, the learning rate is reduced. Then second is the monitor, so it is a quantity to be monitored. And four important arguments that we are using here are factor, patience, verbose, and mode. Let us understand it one by one. First is a factor. Factor is by which the learning rate will be reduced. In general, we can represent it as new LR equal to LR multiplied by factor. LR stands for linear regression. Second is a patience. Patience is a number of epochs with no improvement, after which learning rate will be reduced. In other words, we wait for minimum number of epochs before we reduce the learning rate. So that we specify with this particular parameter. Third is a verbose. It contains integer binary value, either 0 or 1, where 0 represent quiet and 1 represent update messages. And finally, so it will display message. Okay, whenever this particular trigger will execute, it will display message. We will be able to view that. And finally, fourth one is a mode. It contains one value out of auto, mean, and max. In mean mode, the learning rate will be reduced when the quantity monitor has stopped. Decreasing in max mode, it will be reduced when the quantity monitor has stopped increasing. In auto mode, the direction is automatically inferred from the name of the monitor quantity. Next trigger is early stopping. We are interested in only the very best model observed during the training rather than the best compared to the previous epoch, which might not be the best overall if training is noisy. This can be achieved by setting the save based only argument to true. That is all needed to ensure the model with the best performance is saved when using early stopping or in general. It may be interesting to know the value of the performance measure and at what epoch the model was saved. This can be printed by the callback by setting the verbose argument to 1. Early stopping callback will stop training once triggered, but the model at the end of training may not be the model with best performance on the validation data set. An additional callback is required that will save the base model observed during training for later use. This is the model checkpoint callback. The model checkpoint callback is flexible in the way it can be used, but in this case we will use it only to save the base model observed during training as defined by the chosen performance measure on the validation dataset. The callback will save the model to file which requires that a path and a file name be specified via the first argument. The preferred loss function to be monitored can be specified via the monitor argument in the same way as the early stopping callback. For example, loss on the validation dataset. Also, as with the early stopping callback, we must specify the mode as either minimize or maximize the performance measure. Again, the default is auto, which is aware of the standard performance measure. Okay, here I have trained the model for 10 epochs with batch size of 64. It is important to note that usually a higher batch size gives better results like you'll have less computational you will have higher batch size and it gives better result but the expense of the higher computational burden. So some research claim that there is an optimal batch size for best result, which could be found by investing some time on hyperparameter tuning. We are training the model or fitting the model on training data set which is available in TrainGen. Our validation data set is in TestGen. So since our batch size is 64 and total images for training data set are 5234, we will execute total 81 batches of images per epoch. So in this case, our steps per epoch are 81. So for every step, we will obtain loss value and accuracy. Our optimizer will optimize the loss after each batch of the images. Similarly, our validation step will be total test image divided by batch size, which is 64. We are using callback here that we already discussed in last slide. You can observe the output that I got while train the model. You can observe that there are train epochs. For each epoch, total 81 batches of images are submitted for training. For first epoch, total time taken was higher, almost 3152 seconds. That means average 39 seconds per epoch for each batch of images. Okay. Loss we obtained was 0.3473 and accuracy obtained after first epoch was 0.8457, which is 84.57% accuracy for training set. Validation loss observed is 1.0166 and validation accuracy was 0.6267, which is 62.67% for testing set after first epoch. And you can observe that with each epoch, the loss is reduced and the accuracy for training set as well as validation set are increasing. At each epoch, at epoch number 5, the reducing the learning rate trigger, which is part of callback executed, and similarly at epoch 7 and epoch 9 also it was executed. Look at the final outcome we obtain at the end of 10th epoch. At end of the final epoch, we obtain loss value 0.1438 with training accuracy 0.9435. That is 94.35% accuracy is quite high. And however, the testing set accuracy is 0.8698, which is 86.98. Looking at the improvement in validation accuracy, we can observe that if number of epochs are increased, we can obtain higher validation accuracy. So now in next section, we will analyze the results obtained due to this. All right. So very soon we are meeting with the next and final, that means the last episode of this particular lecture, and where we will discuss about the various performance metrics and performance measurement. So I'm sure that you are clear with this particular concept. Okay, and we'll meet very soon with the next lecture series. Okay, lecture part. Thank you very much. Have a wonderful day. We are meeting soon. Thank you.